Hello, this is Mr. Sorrentino here again, doing another Math 31 video, and this one is working on 5.4 properties of logarithmic functions. And one of the properties we were sort of introduced to in the previous lesson, and basically that's the one where we can show that if we have a log base a of a to the x, where the logarithm and the exponential base are right next to each other, means nothing in that space between them, then they just cancel out, leaving the exponent. It works the same way too if you have an exponential raised to a logarithmic base. Again, as long as there's nothing in between them, then they cancel each other out, leaving me with the x right there. So in the instance of these three examples here, they're pretty easy, because log base 5 next to an exponential base 5, this and this cancels. I'm left with 2. This is the same thing as 10 raised to the log base 10 of a. No logarithmic base reported. We automatically assume it's base 10. And again, an exponential base 10 and a logarithm with a base 10 next to each other cancel. I'm left with a. And of course, this is the same thing as log base e of e to the s. And again, same instance here, they just cancel, leaving me with s. So those are pretty straightforward, and that's when we were dealing with situations when we were trying to evaluate logarithms that were actually powers of the given base. We kind of use that and solve for that. This is just a shortcut for that process. Now, if I have other things in between the logarithm and the exponential in some way, I have to deal with that and work with that appropriately. And that's what we're going to be looking at mainly in this lesson is, okay, what if we have a situation when we have maybe, instead of a 10 to the log a power, we have 10 to the 2 times log a power, how we handle that. Or if we have for the log base 5 of 5 squared minus 5. How do we handle that if we can handle that? Or maybe it's better to handle it this way, say 5 cubed. Or, there's going to be different variations that we could possibly deal with in order to hopefully take care of this and come up with an approximation or make our lives easier. So we're going to learn about these properties as we go along with them. Now, as we go into these properties, you're going to see that we have basically what leads up and allows us to make the rule for this. Letting x be the log base a of m, letting y equal to be the log base a of n, and putting these together and kind of showing how the exponential rule applies and creating this logarithmic property. But, ultimately you're just responsible for knowing the properties, so don't feel obliged to know how this proof all works. You just have to know what the property is. And so for the first property, and these properties you should know forwards and backwards, because we're going to make use of them in both ways. They're presented this way because this way is actually the most helpful when you're trying to solve equations with these. Whereas when you deal with situations in calculus, it's sometimes better to spread them out into different logarithms. So this was the product property, which means if I have the sum, notice I have the sum over here of 2 logs of the same base, then I can rewrite that as the log of that base times the product of the two things being logarithmed. I guess I could use that as a word. And likewise, if I have a logarithm of a product, I can write that as the sum of 2 separate logarithms, and the 2 separate logarithms are of the 2 or more things that are being multiplied together before the logarithm's happening. So it's kind of almost like a distributive property, except it doesn't work exactly like a distributive property does. And I want you to be wary of that, because sometimes I'll have students that'll do that. You'll have like a situation where they'll say, I have the log base a of m plus n, and I'll have students rewrite this and say that that's the log base a of m plus the log base a of n. They think that logarithm is distributive. Well, logarithm is not is not distributive. Multiplication is, not logarithming. So we already know that this is actually the product. So this is not correct. And we're going to see instances where students get confused between the rules and things of that nature as well. So be careful, especially when we get into the next one, which deals with the quotient property. The quotient property, let me scooch this over, kind of makes sense. I mean, if I add two logs together of the same base, and that equals the product of those two, well then subtracting two logarithms of the same base should equal the quotient of the two. Please keep in mind, I'll have students that will look at this idea right here and want to say this is log base A of m over log base A of n. Again, kind of distributing that logarithm, but you have to remember this would be what the log of base n of m is. That's not the same thing as this being subtracted. So, don't get them confused. Don't get the change of base formula confused with the quotient property. The quotient property says if I have a single logarithm of a quotient, then I could basically go this other direction here and make it a difference. If I have a logarithm of a base divided by a logarithm of the same base of two separate things, then I can rewrite that as a single logarithm this way. And it's going to be important for us to be able to know, if we want to write things as a single logarithm, what we need to have in front of us to do that. The last one that we make a lot of use of as well is the power property. The power property says if I'm taking the log base A of something raised to a power, so basically I'm taking the log base A of an exponential, then all I need to do is take the exponent and move it in front of the logarithm and make it a multiplication. So these are the three properties that you're being introduced to in this particular section, and basically these examples are going to kind of walk us through how to make use of these examples. So let's have a look at example 2. Here you're asked to express each of the following as sums and/or differences of logarithms. When you get into doing derivatives in calculus, when you eventually get there, you still have to take Math 200 and Math 22, or Math 200 before you take Math 22. But when you get into Math 22, you're in dealing with the differentiation of logarithms. You could take care of the logarithms in this way and do the derivatives as it's written, but it's very, very complicated if you use derivative rules at this point. However, you could rewrite, for instance, A, and I'm going to show you how to rewrite A. I'm going to let you try B. If we rewrite A here, the log base A of x to the 5th, y to the 4th over z cubed. Zoom that back in a little bit. I first notice I do have a quotient, and so I have x to the 5th, y to the 4th divided by z cubed. According to the quotient property, applying it in the reverse that I seen it presented to me, I can rewrite this as log base A of x to the 5th times y to the 4th minus log base A of z cubed. And at this stage, technically, you should really have this in parentheses, but you really don't have to have them in parentheses. When you get expressions that have multiple terms involved, quantities, the parentheses need to be put in there. Still not quite done yet, because this here can be split up some more. And I can split that up by saying, well, by the product property, I'm going to have log base A. Since there's a product in there, I'm going to have x to the 5th plus the log base A of y to the 4th minus the log base A of z cubed. And a lot of students might think that that's good enough for this, but the way the textbook is written and the way what's usually expected of this is that you're asked to show something that shows sums and/or differences of logarithms, nothing with anything raised to a power. So each one of these three terms here term 1, term 2, and term 3 can be rewritten one more time by moving each one of these exponents to the front and making it a multiplication. So I can call this 5 times the log base a of x plus 4 times the log base a of y minus 3 times the log base a of z. And that would be the fully written answer as far as the textbook is concerned. So now what I want you to do is go to B, see what you have there, remember some of your rules about exponents, and rewrite this in a very similar way. Write this as a sum and or differences of logarithms, and then we'll pull this back and go over it. Well, essentially here, I'm doing the log base b of m squared over n times p to the fourth to the 1/2 power. That's what the square root's doing. And so to really make this a little easier, I'm going to square root everything first. And that means that each one of these exponents, knowing that there's a 1 here for the n, it's going to get multiplied by a half. So I'm going to have the log base b of m to the 1/2 power, or take that back to the first power, so I really don't need to have anything there. I was saying m, but thinking n. The n's going to be to the 1/2 power, and of course p is just going to be p squared. Again, I have a quotient, so I can rewrite this as the log base b of m minus the log base b of n to the 1/2 times p squared. And here's why I have to be careful a little bit with this, because this logarithm is going to become a sum, but this sum is being multiplied by a -1. So in this instance here, I'm going to have minus the quantity, the log base b of n to the 1/2 power plus the log base b of p squared. But this negative has to be distributed. So I'm going to have the log base b of m minus the log base b of n to the 1/2 minus the log base b of p squared. And then of course lastly, the second and third logarithms in this expression have exponents, and for this to be considered complete, I shouldn't have any exponents. I should just have sums or differences of logarithms. So I'm going to have, this stays the same because there's no power on that m, minus 1/2 the logarithm of base b of n minus the logarithm base b, well, 2 times that logarithm base b of p. And that would be your final answer for that one. So it's just a manipulation, and sometimes, you could probably do more than one step that I showed at once. However, as you do them, please make sure, that you do enough steps that you can keep track of what you did, and I can keep track of what you did, so if I check your work, I know what it is you were attempting to do at the very least and see how close you got. So, now one type of problem they make use of this with, this idea, is that, okay, well, what if you have a situation like the following? And this is kind of what you had to do back in the old days. I think on the previous video I talked about the fact that, when logarithms were taught at one point in time, not that long ago, mind you. You might think I'm very, very old, but, I'm in my late 40s, so it's not quite that old yet. But, even when I was learning how to do logarithms for the first time, we didn't have calculators that could compute them. There was no log button or natural log button on the calculator. They didn't come until I was probably near my, senior year of high school, Heading, you know, and at that time, the calculators, the graphing calculators and the scientific calculators that had those on them weren't making a mainstay in classes yet. And so when we did logarithms, we had a table of logarithms, and they were just base 10. So if we had to do any other base, we had to use the change of base formula to convert it. And then if we had numbers that didn't fall on that table, we had to use these rules to convert it to something that would be on this table. So for instance, here you're given that the log base A of 2 equals 0.7565. The log base A of 3 is 1.1990. And you're told that the log base A of 5 is 1.7565. You're asked to find the following. And, you know, it should actually say here without use of the calculator. And basically, you really shouldn't be able to do that with the calculator anyway, because you don't know what A is. I mean, so you can't even put that in. So this is basically one that you can't use the calculator to do. So what I'm looking at this here is like, well, I don't have 25, but what I do have is that this is the log base A of 5 squared, which we know from our product, from our power property, that's going to be equal to 2 times the log base A of 5. So if I know what the log base A of 5 is, I could solve this problem, and I do know that. Here's an issue that I see a lot of students do with this type of problem. They're used to substituting numbers into a logarithm, so I'll have students that'll say, okay, this is equal to the log base A of 1.7565. You know, so they'll take a wrong turn and say, I'm going to rewrite this as 2 times the logarithm. Sometimes they'll put the base A in there, they'll skip it, and they'll say 1.7565. That's not the case. I mean, 5 and 1.7565 are not the same number. The log base A of 5 is 1.7565. So when I do the substitution, I'm substituting the 1.7565 in for that number only. And so that's going to be approximately equal to 2 times the quantity 1.7565, which is going to be equal to, and you put that part in your calculator or work it out. I'm going to get 3.513, and that would be the answer. So now we know what the log base A of 25 is. With the log base A of 10, well, I can again, I don't have that listed up here, but I can rewrite this as the log base A of 5 times 2, because 5 times 2 is 10. So I'm going to have the log base A of 2 plus the log base A of 5, because a product becomes an addition of logarithms. And that's going to be 0.7565 plus 1.7565. Probably put the wavy equal sign there, which is approximately equal to 2.513. Sometimes they get a little tricky with these. You know, for instance, this one here, 0.6. You might say, well, how am I going to do this one? Well, yeah, I could say, well, that's the same thing as 6 over 10. I do know a logarithm of 10, base A. But I can even say, okay, well, you know, even in lower terms, this is the log base A of 3/5, because 3/5 is the same thing as 6/10. And I do know what the log base 3 of base A of 3 is and log base A of 5 is. With the quotient property, this is the same thing as the log base A of 3 minus the log base A of 5, which is going to give me 1.1990 minus 1.7565. Again, you don't have to worry about necessarily putting the wavy equal signs in. They're just good to kind of say, hey, I'm approximating here. But, you know, be aware that, you know, it doesn't really matter if you write with the wavy equal sign or not. I'm not going to take any points off of you if you, write it with just a standard equal sign. But that ends up being negative 0.5575. And then D is actually a lot easier if you think about what it's saying. I mean, yeah, you could sit there and say, well, that's equal to the log base A of maybe 2 divided by 2, or you could say 3 divided by 3, or 5 divided by 5. It doesn't really matter. And then use the quotient property. But we know, just from going back to our experience with this, if I simply rewrite this, just call this side x, it's okay, a to the x equals 1. Well, what power of a is going to give me 1? Well, there's only, it doesn't matter what the base is. The only exponent that's going to give you a 1 is if x equals 0. So the log base a of 1 equals 0. It doesn't matter what you have here as the base. If I have any logarithm of 1, it's going to be 0, regardless of what the base is. But as I said, the next thing we're going to be looking at is instances where, like example 4, where now I have a logarithmic statement that's written out in the expanded form, where it's written as the sum and differences of logarithms. Now they want us to put it back into a single logarithmic statement. This is going to become very important for us to do when we start solving logarithmic equations. So it is an important concept to get the hang of. So I have the 2 times the log base x of a plus 4 times the log base x of b minus 7 times the log base x of c. Now again, this is a problem you could not do on your calculator. I want to write it as a single logarithmic statement, which means that I should just have log base x of something, and that's it. So I want it to look like that. So I'm going to start using some of these properties. Now I'm going to be using them in reverse than the ones I had done in the previous problems. I have these multiplication of 2 in front of this logarithm. I have the multiplication of 4 in front of this logarithm. I have a multiplication of 7 in front of that logarithm. I remember that if I had a logarithm of something raised to a power, that exponent became a constant being multiplied to the logarithm. And vice versa, if I have a constant being multiplied to the logarithm, these are going to become exponents on the respective things that the logarithm is affecting. So this is going to become the log base x of a squared plus the log base x of b to the 4th minus the log base x of c to the 7th. Now what I'm going to do is look at this and say, okay, well, I'm going to look at the sum first. Still following my order of operations. I still move from left to right when I have additions, subtractions. Remember, logarithming is its own function. It's its own parenthesis. I don't know what a is. I can't tell you. I can't actually compute what a squared, b squared, and c to the 7th are. And I certainly can't take a logarithm of them because I don't know what the base is, let alone what a squared actually equals either. So I'm going to try to do the addition next. And according to the product property, if I have the sum of 2 separate logarithms, that equals the logarithm of the same base of the product of the 2 terms. So I went from having 3 logarithmic statements down to 2 logarithmic statements. And now I still want to get it down to a single logarithmic statement. So notice that I have this subtraction here of 2 logarithms of the same base, which means I could apply the quotient property, which would say that I can rewrite that as the log base x of a squared b to the 4th, which would be the term in front there, over c to the 7th. And now it's written as a single logarithmic statement, and that's what I wanted. So, pretty straightforward, and there's going to be a lot of manipulation in the problems that you're given from this section to do these various things. So make sure you know what you're doing. Make sure you don't make up your own versions of the rules as you go along with this. Which brings us back to example 5, which is kind of similar to example 1, except we're dealing with situations now, as I mentioned before. For A, for instance, I have the log base q of the square root of q cubed. If I had the log base q and the q right next to each other, things would cancel, I'd be done. But unfortunately, this symbol is running between them. So I can't do anything with that yet. I can't just cause that thing to cancel. So there's a couple things I can do with this. And I can even go a step further to further justify why what we did before was valid. When I look at this, well, q to the third power square rooted is the same thing as me saying the log base q of q to the 3 raised to the 1/2 power, which is the log base q of q to the 3/2 power. Now, as we've done in example 1, having a log base q now right next to a exponential base q with nothing between the two would cancel them out, but just for the sake of argument, let's take this one extra step even though we don't really have to. I mean, I can rewrite this as 3/2 times the log base q of q. And if you think about it, well, if I'm basically looking at this statement here and say, okay, what power of q gives me q? Well, the first power of q gives me q, so technically that's times 1, which equals the 3/2. So that's kind of more of an explanation as to why the cancellation does work. It's because of that, ultimately because of that, that power property, why you can do that. For B, I want you to give it a try and see if you can come up with the correct answer for it. Keep in mind that I don't have a situation yet where the B exponential base and the logarithm base B are right next to each other. This 3 in front of the logarithm is kind of blocking, is in between them and prevents me just from doing a cancellation. Because I'll have students that will just say, and this is the wrong way of doing it, that this is just going to be, well, I'm going to cancel this, I'm going to have equal 3 times 2x, and say that's 6x. That's wrong. So based off of what you've been told by the rules and what I just told you now, come up with what the right answer would be. Okay, so getting back to this now, I gotta move that, I gotta get that 3 from between the b and log base b. So looking at this statement right here, having that 3 in front, I can rewrite that as me having b to the log base b of 2x to the 3rd power. Now I have nothing between these two and I would get my cancellation. So I had the quantity of 2x cubed, and if I'm going to simplify it, I really should just cube both terms in there. So 2 cubed is 8. This ends up being 8x cubed. So common wrong answer for this is 6x. I've seen a lot of students give me answers like that, but the right answer for this is 8x cubed. So for the last one, I want you to take the natural log of e to the x squared raised to the 4th power, as you see it written there, and simplify it correctly and give the right answer. Well, again, the natural log, or log base e, if you want to just, again, think of it as being this, are not right next to each other. I do have this pesky parenthesis right in the way there. Now, there's instances where I really don't need to have that parenthesis, because you could say, well, Mr. Sorrentino, if I had log base e of, e like this, then, I could do that cancellation. Well, there, the parentheses really aren't needed. Here they are, because I do have this quantity being raised to the 4th power. If I just drop the parentheses, I do not have the same thing. And that's where students go wrong with that, is they start dropping things too early and they don't handle it correctly. So what I have to do with this is I have to get rid of this exponent of 4, so I am allowed to drop the parentheses. So I can rewrite this as 4 times the log base e of e to the x squared power. Now what happens is now I have the log base e next to the exponential base e with nothing between them. You know, so there's nothing there. So now they do cancel. I end up with 4 times x squared, which is, of course, is 4x squared. Some students may have chosen, may have done that, you know, in the other way, you know, but make sure you're arriving at this the correct way to avoid making other potential mistakes later. And that brings us to the end of the last example from this video. So for the time being, if you have any additional questions, please make sure to bring them up in class or to come and see me during my office hours. Until I see you in one of those places or until the next video, I'll see you around and have a good day, everybody.